Ci siamo? Funziona il suono? Funziona? Thank you. Good. So lecture number 3. We're going to change register style a lot. I'm going to change style. In fact, I will shift between 3 modes. I mean, more conceptual one, like this morning, and a more physical one, and just mathematics. And I'll try to separate the 3 parts. I am a firm believer that you need all 3. In fact, in recent times, there's a certain habit of disparaging philosophy and philosophical considerations by some physicists of today. That was not the way Einstein or Maxwell or Heisenberg thought. Conceptual thinking is crucial, I think, especially in something like quantum gravity. There's no way of going ahead without trying to think clearly about what we are doing. And you think before, during, and after the physics, not only after the physics. So this to say, do not neglect and think that what we did this morning is not important. In fact, it's enormously important. I think it's what guides then the construction and the use of the theory. So this morning I did a general introduction to quantum gravity, basic idea on which we are building, and a discussion about space. The conceptual discussion is not finished, is not ended, because I will have to discuss time, which is a good discussion by itself and has raised the rivers of ink in quantum gravity. So we'll go back to a conceptual discussion for time and also for quantum mechanics, how to use quantum mechanics in a general relativistic context. But for the moment, let's not do everything together. Let's put it apart and go to math. So I want to either today or tomorrow define the basic structure of loop quantum gravity, its Hilbert space and its operators, at least the kinematics, and then the dynamics later. And I could just begin and introduce mathematical idea as they come in, but it's much cleaner to do the math first, so not to mix things as is often done in physics classes. So let's just do a mathematical piece. And what I'm doing now, it's pretty standard, things that are in books. Some things are pretty elementary, a few are a little bit less elementary, but nothing particularly hard. And but follow carefully, because this all will become equations in the theory slowly. So most of what I'm spending the time today is on the mathematics of SU2. So math, that will be the topic of today, and especially I'm going to describe a number of properties of SU2 and what you do with SU2, because most of loop quantum gravity is playing with SU2. Its representations, the space of function of SU2, the Hilbert space of function of SU2, all this kind of stuff. SU2, of course, is a covering group of SO3, so it's a covering group of the group of rotations, which is a structural property of Newtonian space. But for the moment, we're just viewing it as a mathematical object. SU2 is a fantastic mathematical object. Atiyah, which is one of the great living mathematicians. Once I met him and I was telling about SU2, and then he said, why SU2? And then he answered to himself, well, SU2 is a building block of the universe. It's obviously the building block of the universe. He was saying there are real numbers, they're complex numbers, and there's SU2, nothing else. Which is sort of true in the sense that SU2 is quaternions. It's another name for quaternions. So it's there's something very simple and primary about SU2, but that's not useful philosophy, in my opinion. That's just blah blah blah. So what is SU2? SU2 is an abstract group. So is a set with a a topology and a product, an inverse and a identity. So there is an abstract group, but it's much easier to just describe it as a group of matrices. So let's think of SU2 as a group of matrices. It's easier, so it's a group of matrices, because after all, what we are interested in is structure, which is completely realized by the group of matrices. So by SU2 we mean matrices. So the elements of SU2 are matrices, which we call H. H being a 2 by 2 matrix. 2 is this 2, A, B, C, D, where A, B, C, D are complex numbers. And the matrices are in SU2 are characterized by two things. One, H dagger is equal H to the minus 1. Minus 1 is a standard inverse, dagger is a dagger, so it's a complex conjugate transpose. And the determinant of H equal 1, which is actually two equations, because it's a complex equation, it's a complex number. So it means that the real part is 1, the imaginary part is 0, right? So it's two equations. Now, if you do that explicitly, so if you write, well, let's do it. H dagger is transpose, so A, D, C, B conjugate. And H to the minus 1, you know how to invert 2 by 2 matrices. You have to divide by the determinant, but the determinant is 1, so it's particularly easy. So you just put this here, this here, this here, this here with a minus. That's how you, so you get minus so D, A, C, B, which means that this has the shape A, B, A dagger minus B dagger, A bar minus A bar. So it's actually, there are actually only two complex numbers, but there is this. So A bar, this time this minus this time this equal 1, which gives A square plus B square equal 1. So out of these four numbers, only 3 are independent. So it's a three-dimensional group. So it's three-dimensional. And we see its shape also, right? Because think of this as a real equation. So if you think A is x plus iy and b is z plus ir, this equation is x square plus y square plus z square plus r square equal 1. So this is a sphere in R4, right? In R4, you take an R4 with coordinate x, y, z, and r, R4, and you have a sphere. Not a sphere in 3 dimensions, a sphere in 4 dimensions. So not S2, but S3. So the topology is S3, a 3 sphere. Okay, that's the topology of, which is simply connected, right? On a sphere, any loop you can shrink to. So it's a simply connected group. It's 3-dimensional. And from this perspective, you see immediately that there is a metric, a measure on SU2, which is natural, and in fact is SU2 invariant, which is what? Is the measure, the Euclidean measure in 4 dimension induces a metric on the sphere itself, and that's a metric on SU2, which you can write. I mean, if you can write in terms of A and B. We're not going to write it. I'm not going to write it explicitly. So there is a meaning of DH. You can integrate functions on the group. Okay. It's called the Haar measure, and in fact, I'm not going to prove anything. I'm just going to give statements. I'm not a mathematician. I believe what is written in mathematical books. I don't read demonstration of theorems. I only read the statement of the theorem and I believe it. So this measure is invariant under the action of SU2. Imagine SU2 is this surface of a four-dimensional ball, right? It's if you turn it around, it stays the same. Which means, in particular, that you can do something with it. You can consider functions from SU2 to complex numbers. So a function, if you want a function that depends on h, it's a function of two complex numbers restricted to this region, if you want. And you can define a scalar product between these functions in the standard way and call it psi phi, psi phi. This is standard scalar product notation. So you have a scalar product on the space of function of SU2, and the set of function in the standard way in which you define L2 Hilbert spaces, the spaces of function with a scalar product, you can consider the Hilbert space of functions L2 on SU2. Okay? So this is a set of these functions which are finite under this scalar product. So whose integration on the group itself does not diverge. This is going to be, so it's a Hilbert space of functions, and this is going to be a core tool that we will be using. We're going to use this over and over again, and in fact it's the bread and butter of loop quantum gravity, that Hilbert space. It's on this Hilbert space, or on some collection of Hilbert spaces similar to these ones, one builds the Hilbert space in the sense of quantum mechanics of loop quantum gravity. So keep this in mind. I will describe some structure here. In fact, some key structure here will play a role on. We write a basis. This is I will write a discrete basis on this Hilbert space. We can also write this in Dirac notation, right? This is H, the abstract element of the Hilbert space on the basis, on the continuous basis given by the group element. It's a complex number, which is that. I will soon, today, define other bases here, which are going to be the basis which talk explicitly of quanta of gravity. This will become soon. First, let me say something more. Everybody knows that SU2 has to do with SO3. SO3 is, you don't know what is SO3, it's a three-dimensional group of rotations, so it's an antisymmetric real matrices. And in fact, there is a map. There is a map from SU2 to SO3 which preserves the group structure. The product is sent into the product, but it's not a one-to-one isomorphism. It's only locally isomorphism because it's 2 to 1. 2 to 1. I'll write this map explicitly in a moment. Actually, let's write it explicitly. So let's put an index on these matrices. Let's write this matrix element as HAB. AB, let's put one up and one down. Maybe it's easier. Where A and B take two values. Okay? So let's say 0 and 1. 0 and 1. So the element of SO3 matrix is 3 by 3. So let's call them Rij. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay? Real, not complex, which are rotations. You studied that in primary school. So the map is very simple. It sends HAB into one of these, which, oops, how am I writing this? Into Rij, which is defined as follow, is HAB HCD sigma IAC sigma JBD, where sigma are the Pauli matrices, which you have encountered already, I'm sure, which are three matrices, which are what they are. Forget 1, 1, I minus I, and 1 minus 1. We'll see in a moment. So three matrices. I is 1, 2, 3. I will be Ij will be 1, 2, 3 for me, pretty always. So the Pauli matrices sent one of these 2 by 2 complex matrix into a matrix which turned out to be real. You can check, which happened to be orthogonal, real, three-dimensional, which is this one. We'll give a more abstract interpretation of what is going on here in a moment when we talk about representations and the intertwinings of representations. Now, it's pretty obvious that this cannot be one by one because this is quadratic, and if you take minus h, it gives the same r as h, right? Put a minus here, the two minus cancel. So in the sphere here, the big sphere, so this is SU2. There's one point which is the identity, and there is another point which is minus the identity. Of course, it's in the opposite because minus the identity, you just take the opposite. You have 0 here, 0 here. You take the opposite sign of this. So it's taking the opposite sign of everything. So I'm at 0. So in R4, you go opposite there. So the identity obviously goes into the identity of SO3. Minus identity also goes into the identity of SO3. So by continuity, when you go around, there's an equator here. And this as a whole is SU2, and the upper part is SO3, and the lower part is also SO3. So it's twice. So two SO3 attached, one to the other, which tells you how the things works, because there's a better representation of a three-sphere. If you have a two-sphere, standard sphere, you can think of it as two disks. Right, you take two disks, you glue them by the equator, by the boundary, and you get a two-sphere. So a three-sphere, you have two balls, two three-dimensional balls, full. Okay, so this point here is the south pole, this point here is the north pole, and then you move into a sphere of possible direction until the boundary of this, which is a two-sphere, which is this equator, and which you identify with the two-sphere of this one. And this is SO3, and this is SO3, and there is a natural representation of that. This is identity, and each point is a direction and a length. And a rotation is characterized by an axis around which you rotate and how much you rotate. Right? So, give me any rotation, there is an axis and there is how much you rotate. So the identity is here. This is the axis around which you rotate, how much you rotate. When you arrive at pi, you're here. It's actually the same rotation that minus pi, right? Because if I rotate by pi, it's the same thing as rotating by minus pi, just the same position, okay? But in SU2, no. You just get here, and if you continue, you have all the other route until you get into the to the minus. This is the structure of this group. It's quite useful to keep this in mind then when one where one works. So what about this Pauli matrices? Well, say a little bit more about them. It's pretty easy to show that every matrix of SU2 H can always be written as the exponential I alpha I sigma I, where sigma the Pauli matrix is alpha, there's three numbers. Okay? And this can also be written, this is a simple exercise, is if I write alpha I, so alpha 1 squared plus alpha 2 squared plus alpha 3 squared square root, I just call it alpha, and alpha I over alpha I call it n, the direction and the length. This can be written as cos alpha, the identity, plus I ni sigma I sine alpha. If you just do explicitly, you see that this is the case. This is a useful formula. So the way of thinking about that, the geometrical way of thinking about that, is the element of the group can be obtained by exponentiating this linear combination of things which are in the algebra, and the algebra is actually the algebra is a linear space. So what is the algebra? The SU2 algebra, which mathematicians used to write small SU2, are the object which are linear combination of this. So it's 2 by 2 complex matrices which are anti-Hermitian written with an I, Hermitian without the I. No, the other way around. Hermitian without the I. This is Hermitian, this is anti-Hermitian. So this is a vector space. It's an algebra which has a bracket, and the bracket it's the bracket of the sigma. You know that sigma I, sigma j, sigma 1, sigma 2 is I, sigma 3, etc. The actual basis of SU2, the usual basis of SU2 is not the sigma, but because you want the emission, not the anti-emission, it's called tau I, which is just the sigma I multiplied by minus I half. Yes, half, which have the good property that tau I, tau j commutator, so tau r tau j minus tau j tau r is epsilon ijk tau k. This is the structure of the algebra of little SU2. So you can also rewrite the same with tau and some without I and some real numbers there. It's just normalizations. Now this is a decent coordinatization of SU2, right? This is a natural, reasonable coordinatization of U2. But Euler, who is a great mathematician, but sometimes it's a funny idea, decided to coordinatize the rotation group with the Euler angles, theta, phi, and psi, which I hate. But I write down only because you find everything written in terms of Euler angles. So it's, I don't know, have you worked with Euler angles? I hate them. Do you like them? It's just wrong. I mean, this is it's the right coordination. But anyway, Euler had a bad idea. I just write it because For instance, Mathematica uses this. So if you want to do in Mathematica, so instead of coordinatizing the group with alpha 1, alpha 2, alpha 3, you coordinatize the group with three angles which you call psi, theta, and phi. Which phi? This phi. And it turns out you can always write this as e to the psi tau 3, e to the theta tau 2, and e to the phi tau 3. It's like you rotate in the 3 direction, you rotate in the 2 direction, and then you rotate again in the 3 direction. This is a Euler angles, and you can write the formulas in terms of that. The measure dh in terms of this angle is just the integral in d psi, the integral in d theta, the integral in d phi, with a measure factor which happened to be sine theta. And actually phi goes from 0, 4 pi. Remember SU2 not S O3, theta 0 pi, and psi 0, 2 pi. And if you want the integral on the group to be 1, you can compute it. You have to normalize it, and you have 16 pi square. I just write it for future reference. There's nothing substantial about that. All right. So this is the space. This is the Hilbert space. Now let's go into introduce a key object, which will be our main operator. It's like the momentum operator. This L2 of SU2 will be like the space of the wave functions of a particle. And in the space of wave function of a particle, you have a, what happened to the chalk here? Yeah.
I don't understand where the 4 pi comes from.
The 16 pi?
The 4 pi, why do we integrate up to 4 pi? This is a 4-dimensional ball that we're integrating over?
No, is that if you in SO3, if you do a 2 pi rotation, you go back to yourself. But in SO4, in SU2, if you do a 2 pi rotation, you don't go back to yourself. You just move to an SU2 matrix, which maps down to the same SO3, but is a different SU2 matrix. So you have to have a 4 pi before. So you need a parameter that goes all the way 4 pi to cover. It's related to the fact that if you spinors don't remain the same at a 2 pi rotation, only get back to themselves at a 4 pi rotation. The same thing is that. Oh, I know what happened to the chalk. Good. So key object. We have these functions psi of h. So there is a function on this SU2, and we want to take derivatives. But these are derivatives on a curved space, which is coordinatized in a funny way. When you are in Euclidean space, you have dx, dy, dz, which are preferred derivative operators, which respect the structure. Cartesian coordinate correspond to Cartesian coordinate respect the structure of Cartesian space. Here you have natural derivatives, which correspond to the existence of this algebra. So, if you are in the algebra, you have a direction which corresponds to an element of the algebra is a direction on the group. If you multiply the element of the group here by the same algebra element, you get a derivative here. So you can write a vector field for each direction of the algebra here. So let's do it properly. We define a operator L on the space of these functions, which is a vector operator, so as an index I, 1, 2, 3, is this index I here, so it's direction in the algebra, which is defined as follow, acting on a function of the group. The derivative, so is the limit for t going to 0, 1 over t, the difference minus psi of h. And here you have psi, not of h, but moved there. So h times e t tau I. You multiply this on the right, careful, it's not the same multiplier right to the left, because things don't commute here. And since you multiply it to the right, you call this a left invariant vector field. Now, why you call it left instead of right? Well, don't ask a mathematician. Because it's actually, this is invariant at the multiplication by the group on the left. You can also define another operator with an R and put this on the other side. The two are related easily to one another. This will play a major role in the quantum theory. It will be our main operators. These are three operators, right? Lx, Ly, and Lz. And in fact, they have, it's very much the angular momentum operator. That's what it is. If you take the commutator of two of them, you get the algebra of the SU2 algebra. And the three together, I will also use the notation. So I will also use the notation L with an arrow, meaning the collection of the three of them. It's like a gradient, which is three operators. Good. Fine, right? Questions? Doubts? Everything is clear? Representation theory. This is also something you've seen in elementary quantum mechanics. And it's crucial because the representation play a role every time there is something symmetric in quantum mechanics, right? It's a representation that come in, and also because it's what is going to give us an actual basis on this Hilbert space. So we'll give us the structure of the quantum gravity Hilbert space later on. So representation theory, I'm probably going to say many things that you know already. So what is a representation? A representation is a vector space, V, with a set of matrices acting on the vector space, a map from the group to the space of these matrices that preserve the group structure. So when you multiply two elements of the group, these are sent into the two matrices. A representation is unitary if you have a Hilbert structure, a scalar product on V, so it is a Hilbert space, and the representation matrices are unitary. Is irreducible if when you act with a group, there are no invariant subspaces, and two representations are inequivalent if there is no unitary mapping from one to the other, such that it's an isomorphism. And you can list all the unitary inequivalent representation. Mathematicians have done that for all groups. It's a beautiful piece of mathematics. And in particular for SU2, the irreducible, the irreducible representation are labeled, are listed, are labeled by a quantity that conventionally is called J, and conventionally has values 0, 1/2, 1, 3/2, and so on. This is conventional, right? You could call them 0, 1, 2, 3. It's just historical, and it's called spin. Spin. And the representation matrices are function of a group element, and there is a family for each j and have matrices or indices m and n here. Now what you learn from the mathematician, the list of all the representation, is that the representation j, so the linear space Vj is a Hilbert space because it's a unitary representation, have dimension 2j plus 1. So the dimensional space is 2j plus 1. So these indices take 2j plus 1 values and are traditionally taken to be minus j plus 1 all the way to plus j. And these are 2j plus 1 because of j negative, j positive, and 0. And so this gives a basis. This index labels a basis here, which is almost always, but not always, taken to be the eigenvalues for Lz. It's defined to be the basis where Lz is diagonal. So these are matrices, 2j plus 1 times 2j plus 1, which depend on the h, which are known explicitly. And how do you compute them? It's very easy. You go to Mathematica, you type thing, and it gives it whatever it is. So it's, you don't have to recompute them. Or you go into boring books and they explain you how to compute them, but I think I've done it once when and I forgot. In Mathematica, these are called Wigner, what they're called? Wigner D. And they're written as Wigner D, capital D, and then you have to put j, m, and n, and to be sure that m and n are between. These are integer. You put j or 2j? J.
J.
So this has to be half integers. This has to be an integer between. No, this also has to be half integers between minus j plus j, and then you have to put the Euler parameters, psi, theta, and phi. This is why one has to know the Euler angles. So in case you want them explicitly, you just type on Mathematica and you can see what shape they are and what things they are. Now, these are key objects. These are very key objects because of a theorem, which is a very general theorem. It's called the Peter-Weyl theorem, which is a structural theorem about the harmonic analysis on a group. SU2 is a compact group. You can do harmonic analysis in a compact group, and these are the key objects. And what is going on is it's very simple. Think about Fourier transform on a circle. Right? You know that on a circle you can write functions on a circle, and you can expand in a basis. The bases are the plane wave, the e to the I n phi. Phi is the angle. So e to the I n phi is a basis on the circle, or the function of the circle. But the circle is also a group, is U1. It's a compact group. And this n labels the irreducible representation of the circle. So representation theory gives you a way to write discrete bases with a lot of good properties, which I'm going to exploit, on the space of function on a compact group. So this is blah, blah, blah. Let me do it explicitly. Here's a theorem. It's the Peter-Weyl theorem in all its splendor. I'll write it in two or three forms because it's a theorem. Peter-Weyl. D, J, M, N of H, seen as an element. So this is an element of L2 of SU2. So the space of functions, these are have finite norm, and these so for each j, m, n, you have one of these, and the set of these form a orthogonal basis of that space of L2 of SU2. So let's put it in formulas. This means that the scalar product of two of them, the integral in dh of dj m n of h bar dj prime m prime n prime of h, okay, is 0 unless all these are the same. So delta j j prime, delta m m prime, delta n n prime. And if they're equal, you're going to say, well, it's 1. No, it's 1. I didn't say that it's orthonormal. I only said it's orthogonal. So in fact, it's not 1. You have to normalize to get 1. But the normalization is simple. It's 1 over 2j plus 1, the dimension. So you can think of this object here, dj m n of h, in the way you think in quantum mechanics, e to the I k kn. Let's say we're in a circle, so k is discrete. Sorry, k alpha. Alpha is the angle of the circle. This is a state k in the representation alpha, and this is a change of basis between the continuous basis alpha and the discrete basis k on the L2 space for a particle in a circle, quantum particle in a circle. Are you with me? Okay. So you can think this is the same way, h and a state j m n. And this is a orthogonal basis. And if you just multiply by the dimension, the square root of the dimension is an orthonormal basis. So like that is just orthogonal. If you multiply by square root of 2j, if you multiply this thing here by square root of 2j plus 1, is actually a orthogonal basis. This 2j plus 1 is deadly when you actually sit down and do calculation in quantum gravity, because you always going to get it wrong all the time. To go back why things don't work, and then you realize that you forgot the 2j plus 1. But just being careful. Let's find another way. Oops, time fly. There's a third way of expressing the theorem, but it's 45, so let's stop here, and I'll do it after a break. I don't want you to get tired. I don't want to go over 45 minutes. There are studies that after 45 minutes the tension goes down. So let's break it here and restart at 5 sharp.